Okay, so in this video, I just want to use the technique that we learned in the previous video, namely the method of integrating factors, and just execute on it on some examples. Okay, so just as a quick review, remember a first order linear differential equation is one that can be written in this form right here. Y prime plus some function of x, p of x times y equals q of x. Okay. Um, no assumptions so far about what P and Q are, what they are, but uh, this is our starting point. This is the equation that we wish to solve. And we talked about the method of what's called integrating factors. The integrating factor is this function r, which recall we multiply both sides of the equation by, and this resulted in the left-hand side being expressible as the derivative of something. Once we have the left-hand side expressible as the derivative of something, we can then integrate and do some other stuff to arrive at the general solution. Okay, so this is the tech we're going to use in doing our examples here. So let's start with a really simple one. I'm just pulling exercises from the textbook. Let's I can write. Let's do y prime plus xy equals x. Okay, now this is written for us in the form of a first order linear differential equation. It looks exactly like what we have up here, the sort of general form for such an equation. Just to be absolutely clear, we can identify, for example, that what's playing the role of p of x here is x, and what's playing the role of q of x is also just happens to be x. This is just a coincidence, or this is just particular to this problem. Okay. What the boxes above tell us to do is to first find something called the integrating factor. So let's do that first. R of x is going to be x of an antiderivative of p of x. Now, p of x here is just x, so I'll go ahead and write this. And I want to emphasize this notation here, it departs a little bit from our let's say single variable calculus experience, and the reason is because what this is referring to is not the set of all antiderivatives of x, which is the usual notion of the indefinite integral. Rather, this is referring to a specific or a particular antiderivative, any particular antiderivative. In other words, we can take any antiderivative of x that we want here. So I think I'll go ahead and take the simplest one, 1/2 x squared. And note that I'm not writing plus c, okay? I'm not doing that. R of x is not a general, there's nothing, it's a very particular function that we are choosing in order to kill the problem. In this case, it's going to be x of 1/2 x squared, okay? 1/2 x squared is an antiderivative of x, hence this is what we get. I'm not writing plus c here. You see that? That's the point I'm trying to make. Okay, so there's r of x, and now immediately from that, I can write down the general solution. Y of x is equal to 1 over r, so it's 1 over x of 1/2 x squared. Now don't forget what exp is. Exp is just e to the 1/2 x squared. Okay. Now I want you to imagine me taking this r right here and putting it underneath 1, taking the reciprocal of it. That's 1 over r, right? Isn't that the same thing as just multiplying the exponent by -1? Right? That's the same thing as taking a reciprocal. So I can rewrite this as y equals e to the -1/2 x squared. That's my 1 over r times the integral of r times q. So what's playing the role of r here? Oh yeah, it's e to the 1/2 x squared. And then what's q? Q is x. Look here, we identified it for ourselves. Q of x is x. So I can put that x right here. I feel like I have to put it there as opposed to putting it on the other side. I think because I have mental issues, but that just looks right to me. Okay, good. We're not done yet because we can kill this integral. How to kill this integral? The way that we kill this integral is through u substitution. we're going to let u equal 1/2 x squared. Then du is equal to, I think it's x dx. All right. And we can continue here. We have e to the negative, or I'm going to write it as exp of negative 1/2 x squared times now, and I'm going to open up a big old bracket. No, I'm not. Actually, I'm going to go ahead and do the u substitution. I'm going to do the u substitution on this integral, and I get the integral of, I think I get just e to the u du. Does that look right? I mean, I've got here my du. It's that fetus looking thing there. And the middle part is e to the u. Okay, so we get this. And if I continue, this part doesn't change. I don't need to do anything to it. Times, and now I'm going to open up a big old bracket. The antiderivative of e to the u with respect to u is e to the u plus c. So that's e to the u. But remember what u is? It's 1/2 x squared plus c. And I close bracket. Oh, I'm mixing up all sorts of notations, but hopefully you can deal with that for the exponential function. Now I can do better than what I've got here by distributing the exp. Okay? Because notice that what happens when I distribute this term here over this plus, this thing and that thing collide, that thing and that thing collide. And please notice that exp of negative 1/2 x squared times e to the exp of 1/2 x squared, those things, they cancel each other out, right? And what we're just left with is 1. And then we have plus c times exp of negative 1/2 x squared. And this is the general solution. So in particular, if we set this constant c equal to 0, then we get the solution y equal to 1, or the purported solution y equal to 1. Can we just check with our eyeballs that y equal to 1 really is a solution? We'll go back to the original equation and plug in y equal to 1. Y prime is 0. X times 1 is x. And oh my god, it's equal to x. Okay. So indeed, when c is equal to 0 at the very least, this is a solution. And you can check, no matter what c is, this will be a solution to this differential equation. Great. This is the general solution. Is this clear? Okay, this is the game. It really just boils down to doing 2 integrals. That's it. Okay, let's do another example. Let's do, how about an initial value problem? Okay. An initial value problem. Let's do y prime plus 3x squared y is equal to sine of x e to the negative x cubed, good God, with y of 0 equal to 1. Okay. Well, what's playing the role of p of x here? It's always good to identify these things for ourselves. So p of x is 3x squared, and q of x is sine of x e to the negative x cubed. Remember, the general form for a differential equation, a first order linear differential equation, is this. And with this in mind, we can bring our example into compliance with the differential equation that we see in this box by choosing p of x and q of x in this way. Okay, then the integrating factor, which I think I was doing in blue, is r of x. This is exp of an antiderivative of 3x squared dx. And what does this end up being, of course? This ends up being exp of x cubed, e to the x cubed. Okay. Nice. Then what is the general solution? The general solution is 1 over r, so that's exp of negative x cubed. Think about that negative sign there, times the integral of r times q. Yeah, so maybe I should rewrite these formulas. So remember, r is equal to exp in general of an antiderivative p of x dx. I'm working from memory right now. I hope I'm not messing it up. And then we have r, or no, I'm sorry, y, which is 1 over r times the integral of, I forgot. Oh, no, I didn't forget. It's r times q dx. Okay. So this term right here is 1 over r. And then we're going to do r times q. R times q. So there's r. Q is right there. Oh, do you see this is a textbook problem. It's really concocted here, quite artificial. You see this x cubed, when we multiply r by q, this x cubed is going to cancel and annihilate this e to the negative x cubed. And so we're going to be left with the integral of sine of x dx. This is easy peasy now. What is the integral of sine of x? That is, oh god, I think it's negative cosine of x plus c. Notice, so you have to keep it straight. In the integrating factor, because we're looking for a specific function, we don't write the plus c, right? This thing here is an antiderivative. An antiderivative. It's not named an. An is a article. An antiderivative. Whereas here, we do include the plus c. Okay? And the reason is because here we're looking for the general solution to the differential equation. We want all antiderivatives of r times q. Okay? So keep that straight in your head. And now we distribute the exp, and what we get is exp of negative x cubed times, oh, and I'll put the negative sign out front because I have mental issues, cosine of x, like this, plus c times exp of negative x cubed. Do not forget that c also gets touched by this exponential. And this is the general solution. Oh, sorry, this is the general solution. I shouldn't have boxed this because this is an initial value problem that we have before us. We cannot forget that we also have an initial condition here. Okay, so that initial condition is going to allow us to pin down a particular value of c that meets the specifications of the initial condition. So let's incorporate that initial condition. Let's look at y of 0 equal to 1. So if y of 0 is equal to 1, that means 1 is equal to y of 0, which is equal to, now, negative exponential of 0 times cosine of 0 plus c times the exponential of 0. That's just me plugging in x equal to 0 everywhere in the general solution. Well, exp of 0 is 1, cosine of 0 is 1, so this becomes negative 1 plus c. We add 1 to both sides and we learn that c is equal to 2. And now putting things together, we learn finally what the particular solution is. It's y of x is equal to negative the exponential of negative x cubed times cosine of x plus 2 times the exponential of negative x cubed. And you could factor out the negative x or the exponential bit. There's an exponential factor common, but I somehow cannot be bothered to do that right now. Okay. One more example, and then we'll call it done, cooked, and over. Sometimes you're going to be given examples which you need to do just a touch of manipulation with. Okay. So let's solve the differential equation 1 over x squared plus 1 times y prime plus xy equals 3. And we won't put it in initial condition, okay? So this is our differential equation. Now, it would be a mistake to immediately try to figure out from here what P of x and Q of x are without doing a little bit of manipulation beforehand. Because this is not in compliance with the general form that we've got here. Right? Because we have something which isn't equal to 1 in front of the y prime. So what we need to do is manipulate this expression to get it into compliance with this general form here. Because once we get it into compliance, that's what makes the machine of integrating factors work. Okay? So what we're going to do, of course, is multiply through by x squared plus 1, both sides of the equation. If we do that, we get y prime. Oh, let me write this as work that we're going to do here. This is going to be y prime plus, now x squared plus 1 times x times y is equal to 3 times x squared plus 1. You understand what I did? I multiplied both sides of this equation by x squared plus 1. And then now I can identify everything. Maybe I'll just clean it up a little bit. Do I really care? I can't tell. Maybe I don't care, but I can't tell. I don't want to think about it. So I'm just going to mindlessly grind like this by distributing stuff. And now I'm going to identify my P of x to be, here's my P of x, this, and here's my Q of x, that. Okay, now I'm going to write down my integrating factor. Was I doing that in blue, I think? Of x cubed plus x dx. And I think this becomes the exp of 1/4 x to the 4th plus 1/2 x squared. Easy peasy. That's my integrating factor. Don't forget the logic. If I multiply both sides of my differential equation by this, and when I say it, my differential equation, I mean my differential equation in this form. If I multiply both sides by this r of x, then the left-hand side becomes the derivative of something, of namely r times y. Then I can integrate both sides, then I can divide by r, and then I win. And what I end up with is that y, God, go away. Okay, sorry. Y is equal to 1 over r, so the negative of this, so exp of negative 1/4 x to the 4th plus 1/2 x, oh no, minus 1/2 x squared. Be careful with your minus signs. Times the integral of, oh my God, really? Really? Oh, let's see what happens. I'm a little scared. So r of x, which is exp of 1/4 x to the 4th plus 1/2 x squared times 3x squared plus 3. Hmm. Okay. I believe, having never seen this problem before, I believe that we are going to now run into a bit of an issue. And the issue is that this integral right here is one of those famously intractable ones. When you have thing like, let me just think this through. It could be that this is killable using a combo of integration by parts. Do I believe that? Minus v du. Well, let me end this video here because it's already 20. Oh, and let me make the comment. When you run it, sorry, I kind of spaced out there. When you run into an integral which you believe is not is one of those intractable integrals. And I kind of suspect that this is, but I'm seeing that maybe there's a way out. And maybe what I'll do is spend another video, totally optional, trying to solve this integral, just because I want to satisfy my own curiosity. And why not let you just show you? Why not show you that? But when you do run into this situation, the thing to do is just leave your answer in this form. Okay, just leave your answer like this because you can't do any better because this is kind of accepted to be impossible. Now, if when we say that it's impossible, well, what good is that? You know, like what good does this do for our lives if we can't evaluate something like this? The thing is that it is extremely useful to know that your solution is of this form, even if you can't explicitly evaluate the integral. And the reason is because you can use computers to numerically estimate certain aspects of the integral, or for certain values, you can use computers to numerically estimate. So even though I can't write down, or I don't know if I can write down a really explicit answer for this integral here, I'm I'm pretty satisfied. I'm pretty happy because I've got something now which I can feed to my computer and have that do its beautiful computer work, and make the computer happy, and as a result make ourselves happy. I don't know why I needed to say that. Okay, anyway, I'm gonna stop this video here. Hopefully you understood what I was saying. It takes some judgment to determine when an integral is impossible or intractable, but I suspect this one is, but I'm not sure, and I'm going to do a little investigation in an extra video. Okay, see you in that one. Totally optional. If you don't want to look at it, don't watch it. Okay, bye.